So we're now ready to tackle the simplest possible problem we can deal with. We're going to look at the free particle. This is a particle that's it's moving in one dimension, okay, and the potential energy is zero everywhere. That means along the x, let's just say it's along the x-axis, that dimension. Along the x-axis, it's not experiencing any force at all, so its potential energy is constant. Okay, what's our Schrodinger equation? Time independent, do you remember? H hat psi equals E psi. Okay, and that's always going to be your first thing you're going to try to solve. You solve for stationary states by solving the time-independent Schrodinger equation. So H hat psi equals E psi. What is the Hamiltonian operator? That's kinetic energy plus potential energy, right? Well, what's the kinetic energy operator? Negative h bar squared over 2 times the mass times the second derivative with respect to x, right? And potential energy operator is 0. It's a multiplicative operator in this case. It's 0. So h hat psi then is negative h bar squared over 2m second derivative with respect to x operating on psi. So that's your h hat psi is equal to E psi. This is your differential equation. And let's rearrange this to something that is a little bit familiar. I'm going to move my m and my h bar squared on the right. So what do I have? Second derivative of psi with respect to x equals, I'm going to move my m over there. So it's going to be 2m times E, right? And my h bar squared, I'm going to move over there. So that's going to be over h bar squared, and that's going to be negative, right? Times psi. And this is just a constant, right? And so move everything to the left. I can rewrite second derivative of psi with respect to x plus 2me over h bar squared psi equals 0. Okay, so this is like ay double prime plus 0y prime plus cy equals 0, right? So what's your a? 1. What is your c? That constant right there, and b is 0, right? So what's the general solution to this? What's our s? S equals plus or minus 0, negative 0 plus or minus 0 squared minus 4 times A is what? FC is 2me over h bar squared divided by 2. And so that's negative of plus or minus, okay, negative 8 me over h bar squared. Now, mass is positive, energy is positive, h bar squared is positive, so this expression here is positive. So I have a square root of a negative number then, right? So I can factor out square root of negative 1, so that's going to be plus or minus I times square root of 8me over h bar. And I forgot, I have that divided by 2 down here. Okay, I'm going to move my 2 inside, okay? So what happens if I move my 2 inside my square root sign? It becomes a 4, right? So plus or minus I square root of 8me over 4 over h bar. So that's equal to plus or minus I square root of 2me over h bar. So those are my two possible s values. Positive I square root of 2me over h bar and negative I times square root of 2me over h bar. So what is the general solution to the Schrodinger equation for a free particle? We say psi as a function of x is equal to some constant c1 e to the I kx, where k is this one, right? I'm getting lazy, so I'm just going to call this one k. K is square root of 2me over h bar plus c2 e to the negative I kx, right? And so that is your general solution to the Schrodinger equation for a free particle. Right? And since it's a free particle, there's no restrictions on it. That's the solution. Okay. So that's just a review. Psi is some constant a e to the ikx plus another constant b times e to the negative ikx. What did we say k was? Square root of 2me over h bar. Okay? Alright. What are the allowed energies? How is the energy related to kh bar? To k. How do I solve for k? Energy. So k is square root of 2me over h bar. So if I want to solve for energy, what do I have? K and h, and then you square it, right? So k h bar squared over 2m. Alright? There's no restrictions. Energy can be anything, right? K can be, there's no restrictions. It's a free particle. No quantization. Okay?